Good morning, student. In this class, we are going to discuss the wave equation of a vibrating string. Wave equation of a vibrating string. Okay. Suppose a string is vibrating this way. Okay. So this is at one moment of the vibration of the string. We freeze time here, and this is y-axis, and we have plotted the displacement as a function of the position. Okay. Now, since as I have told you, this vibration of a string is a transverse wave. That means the displacement of the element of string or the displacement of any length element of the string will in a direction perpendicular to the propagation of the wave. Suppose if the string wave is propagating in this case in the x direction, therefore the vibration of each element of the string, suppose we are considering an element dl here, say this is at a distance x and x plus dx. So basically we are considering a delta x length of the string, then its vibration with respect to position as well as time will be in a perpendicular direction to x, that is in the y direction. So we are considering a transverse wave here, and we are going to find out the wave equation for a transverse wave. And you will be surprised to see that the transverse wave also follow the similar kind of wave as the longitudinal wave does. For example, in case of a sound, we have derived the equation of the wave for sound wave, and the transverse wave will also going to follow a similar kind of a pattern. Okay, now to evaluate the equation of motion for a vibrating string, we assume some assumption. Number one is that, say, the force of gravity has no effect on the equation of motion. Okay, first let's assume that the gravity does not have any effect on the equation of the string. So first let's assume that. Next, say the string is uniform. The string is or homogeneous, say homogeneous, that is mass per unit length of the string is same everywhere. The string is same. So if rho is the mass per unit length of the string, therefore we are considering an element delta x of the string. So therefore mass of that element delta x will be equal to rho into delta x. We can write this expression because we are considering that the string is homogeneous, that is mass per unit length is same throughout the string. Okay, so this is the second assumption which we have done. Okay, so with this assumption, let's find out what is the equation of motion of the string. Okay, so first let's have an extended view of this part. Say this is P and this is Q. Okay, so if we plot it in two-dimensional case, then this is, say, x-axis, this is y-axis, and suppose this is the extended view of the portion PQ. So if this is P and this is Q, this is at the P point is at the point x and Q point is x plus dx. Okay, so now if the string is vibrating like that, as you already know, there will be always a tension opposing the equation of that string. So at the point P and Q, there will be tension acting on the string. Okay, suppose at the point P the tension is acting. To find the value of tension, we have to draw a tangent line at that point. So suppose this is our tangent at the point Q, and say it's making an angle beta. Say this angle is beta with the x-axis. So say this tension is, the value of this tension is T2. Okay, now at the point also P also, there will be tension acting on that point, and say this direction of the tension will be along this direction, and we say this tension is T1, and it's making an angle say alpha. So this angle will be basically alpha, which it makes with the at the point P. Okay, so this is the only force we assume, because tension is nothing but a force, and we have ignored gravity. So basically this will be the only force acting at the two end of the string. Okay, and we are considering that the length of the string is delta x, which itself is a very small quantity. Okay, so now what we are going to do, we are going to resolve the tension into two components. In the x direction, the component will be T2 cos beta, and in the y direction, that component will be T2 sin beta. Okay, similarly for this tension T1 along x direction, the component is T1 cos alpha, and along y direction the component is T1 sin beta, sorry, T1 sin alpha. Okay, so when the string vibrate in the y direction, we will not consider any displacement along the x direction. Now you see, along the x direction, two forces are acting, T2 cos beta and T1 cos alpha, and both of them are in opposite direction. So this force must be balanced by this force, otherwise there would be a displacement along x-axis, which we neglected, but or which we don't consider, since it is a transverse wave. Okay, so from here we can write T2 cos beta is equal to T1 cos alpha. Say this is equal to T, where T is nothing but the tension on the whole string. Okay, so T2 cos beta is equal to T1 cos alpha is equal to say T. Okay, so this is say equation 1. Okay, now let's consider, this is the x part of the equation. Now let's consider the y part of the equation. Then in the y direction, the force is T2 sin beta, okay, minus T1 sin alpha, because these forces are in opposite direction, and since we are considering the displacement along the y-axis, therefore this must be equal to the mass into acceleration in the y direction. This is nothing but Newton's second law of motion. Okay, and now let's, in y direction, the displacement of the string at that point is equal to u. Okay, so the acceleration in normal case, it would have been d2u by dt square, because if we differentiate displacement twice with respect to time, you will get the acceleration. But in this case, you should keep in mind that u is a function of both x and t. Okay, but u depends both on the x as well as t, both it's periodic function of both x and t. Okay, therefore in the when we represent acceleration, then we have to write a partial differentiation of u with respect to time. It means u not only depends on time but as well as x. Therefore, when you differentiate with respect to t, we assume x at a constant x. Okay, that is the meaning of the partial differentiation. Okay, now the mass of the string of this part, we already considered rho into delta x. Therefore, what we will write, T2 sin beta minus T1 sin alpha is equal to rho into delta x, okay, del 2u over del t square. So this is equation 2. Okay, so now from equation 1 and 2, what we are going to determine, we are going to determine the equation of motion for this vibrating string. Okay, so let's concentrate on that part of the derivation. Okay, so we know that T2 cos beta is equal to T1 cos alpha is equal to T. We know it. Okay, next we know T2 sin beta minus T1 sin alpha is equal to rho into delta x into del 2u over del t square. Now what I am going to do, I am going to divide T2 sin beta with T2 cos beta, T1 sin alpha with T1 cos alpha, and rho delta x with t. These three quantity have the same value, therefore we can do it. If it is different, then we cannot do it. Since these are same value, then we can easily do it. Okay, so what we will write, T2 sin beta divided by T2 cos beta minus T1 cos alpha over T1 cos sin alpha, okay, rho into delta x over t, okay, into del 2u over del t square. Okay, so this thing we write tan beta minus tan alpha is equal to rho into delta x divided by t, okay, del 2u over del t square. Okay, now suppose this is a function y with respect to x. Okay, now the tangent to at any point of the function, suppose this is a tangent and it's suppose make an angle alpha, so we can write tan alpha is equal to nothing but del y by del x. Okay, so we can always write tan alpha is equal to del y by del x. Okay, now in this case we have replaced y with respect to u, because u is nothing but a displacement in the y direction. So basically u is you can assign any value of y. Okay, so this thing del y by del x, we can also write del u by del x is equal to tan alpha. Okay, so from here what we can write, tan beta, in this case we can write del u by del x at the point where, because remind you beta is the angle at the point x plus dx. Okay, so this is nothing but the derivation of u with respect to x at the point x plus delta x. Okay, minus tan alpha, you see alpha is an angle at the point x, therefore what we can write, tan alpha is equal to del u by del x at the point x is equal to what we can write, this is for your reference. Okay, we can write rho into delta x over t del 2u over del t square. Okay, so what we can write now, we can divide the whole thing with respect to delta x. Okay, so delta x del u over del x, this is x plus delta x minus del u by del x at the point x is equal to rho over t del 2u over del t square. Okay, now we will take the limit as delta x tends to 0. That means the difference between the both ends of the string is very small. We are considering it for a very small part of the string, and if the small part satisfy one equation, then whole part of the string will satisfy the similar kind of equation. So it's a very, we can choose it arbitrarily. Okay, so if we let delta x tends to 0, then del u by del x at the point x plus delta x minus del u by del x at the point x is equal to rho by t del 2u over del t square. So if you remember, this is the classic definition of a differentiation of a operator. Here that function is del u by del x. So basically what we have to do now, we have to differentiate it with respect to x. So this is the meaning of this expression. Okay, so del by del x, del u by del x is equal to rho by t del 2u by del t square. So this is the differentiation double. So del 2u by del x square is equal to rho by t del 2u by del t square. So this is nothing but the equation of the vibrating string. Okay, so this is the equation for the transverse wave, because vibration of a string always a transverse wave. Okay, now let's see the unit of this unit of this quantity rho by t. So rho basically is nothing but mass per unit length, so kilogram per meter, right? And t is nothing but force, tension is nothing but force only, so that is kilogram meter per second square. Therefore rho by t will have the unit kilogram cancel out, so meter will become this side, so basically that is second square over meter square. So meter per second is a unit of velocity, so this is 1 by c square only. This is nothing but the velocity square. Okay, so therefore we can write the equation of a string as, if I rewrite this equation, it will be of this form: del 2u by del x square is equal to 1 by c square del 2 u by del t square. This is exactly the same equation which you obtain for the longitudinal wave. Okay, so whether it's a longitudinal wave or a transverse wave, it's always going to satisfy this form of the equation. This is one of the most important and beautiful equation of physics. It can explain each and every aspect of a wave motion, that is a periodic motion. Okay, so for even for a vibrating string which are transverse in nature, the equations that is followed by the string will be always del 2 u over del x square is equal to 1 by c square del 2 u by del t square. Okay, so in the next part of the video, I am basically just going to write the equation which is satisfied by this wave. I already have discussed about the wave equation satisfied by this kind of wave equation. I am just only going to repeat it again for your convenience. Okay, thank you. In the last part of the video, we have discussed about the equation of motion of a of a string, equation of motion of transverse vibration of a string, and it was given as del 2 u over del x square is equal to 1 by c square del 2 u over del t square. Okay, where u is the displacement of a particular element of the string. U is the displacement of the element of a string in y direction, right? Okay, so we have already solved or we already know the solution of this kind of equation, and it is basically a sinusoidal or cosine function of u of time and space. So we can write u is a function of the sine or cosine. We have already discussed about that. Say u is equal to a sine omega t minus kx. Okay, the cosine function will also do the same job. If you plug it in this equation, then we can see that it will satisfy this differential equation. Okay, here we know that c is equal to omega by k, nothing but the phase velocity of the wave. Okay, so we can do little bit modification. For example, here say if we take omega factor out of this equation, then what we will find? Sine omega t minus k by omega into x. Okay, so k by omega, we know it is nothing but the velocity or the phase velocity of the wave. Therefore we can write sine omega into t minus x by c. Okay, so t minus x by c, this expression we can write. Okay, so this is one of the many ways to write the wave solution, and this is also one of the many ways to write the wave solution. Okay, so we can do a little bit of more modification. For example, omega we can express it with respect to the frequency of the wave. For example, we know that omega is the circular frequency, therefore omega is equal to what we can write? Twice pi into nu. Okay, and k also we can write twice pi over lambda. Okay, so we can also plug it these two expression here, and we can write different sort of wave solution. For example, if you input the value of omega and k here, so let's see what solution we'll get. Sine twice pi nu into t. Nu is nothing but the linear frequency and omega is the angular frequency. So in place of k we can write twice pi over lambda into x. Okay, so twice pi we can take the common a sine, so what we will get? Twice pi nu into t minus x by lambda. Okay, so a sine twice pi nu t minus x by lambda, also one type of a solution of this equation. So a sine twice pi nu t minus x by lambda, this is another expression. Okay, for the same solution. Okay, so 1, 2, and 3, they both mean the same thing, but it's other, I mean, it's another or fancy ways of writing the wave solution. You can use it as you please. I mean, there's all three solution meaning the same thing. Even we can write something like that also, or I mean, I put it as a homework for you to show that you can also be written as a sine twice pi over lambda ct minus x. Okay, thus you have to take this lambda factor out, and as you can see, mu by lambda is nothing but c, because unit of nu is equal to, we know, 1 by second, and unit of lambda is equal to meter. So basically it is inverse of that quantity, so you can also write it like that also. So it's, I put it as your homework in order to prove that you can also be written as a u is equal to a sine twice pi over lambda ct minus x. So this is the fourth expression. Okay, so whenever you have to write the wave solution, so either you can write it in the form of equation 1, or in the form of equation 2, or in the form of equation 3, or even in the form of equation 4. So you can use alternatively all this definition, but for the derivation purpose, I will basically stick with this definition because this is the simplest one, and we can derive all other forms of wave solution from this expression. So I'm going to use this expression for derivation of total energy of the string, and also for many other things. Okay, so just do this homework and prove that you can also be, the displacement of the element can also be written as like that. Okay, so with this I wind up this part, and I hope you understand. And as you can see, the transverse wave or the longitudinal wave, they have similar kind of solution, and they also follow similar kind of wave equation, right? This is the most important part. Longitudinal, transverse doesn't matter, it always follow similar kind of wave motion. Okay, so in the next part of the video, what I'm going to do, I'm going to find out the total energy of a vibrating string. Okay, so as you can see, when a string vibrate, or when a wave passes through the string can have the kinetic energy or even the potential energy. So the total energy of the string will be the sum of its kinetic energy and the potential energy. So I'm going to basically calculate what is the value of total energy of a vibrating string. Okay, so next